In this discussion, we're going to talk about logarithms and then logarithmic functions. So let me start out just with some notation here. The logarithm of 16 base 4 is equal to 2. Again, that's read, the logarithm of 16 base 4 is equal to 2. Or sometimes that's read, log base 4 of 16 is equal to 2. What this means is if we take the 4, by the way, this is called the base. We take the base and we raise it to the power that's right there. That's an exponent to the second power. Then it's equal to the number that's here, which is called the argument of the logarithm. So the log of 16 base 4 equal 2 is just another way to write 4 to the second power is equal to 16. So in more general terms, we'll see this. The logarithm of an argument x, and x could be a number, it could be an expression, it could be a single variable, base a is equal to y. If and only if, meaning they're equivalent, if and only if the base a raised to the power y is equal to x. Those two are similar. We call this the logarithmic form. And we call this the exponential form. Now, the base of these logarithms is similar to the bases of exponential expressions or exponential equations. And in fact, you see that's what we have on the right side, a to the power y, where a, of course, is the base, y is the exponent, and x is what that power is equal to. So there are a few things that we deal with here. A has to be positive, it has to be greater than 0, and furthermore, a cannot be equal to 1. It's just because that's not interesting. So another way to write that is to say that a is between 0 and 1, or a is greater than 1. Those are the types of bases that we're allowed to use. So one of the skills that we need to deal with is changing from one form to the other, changing from logarithmic form to exponential and vice versa. So we will be dealing with problems, certainly in the homework, that go something like this. Write the following in exponential form. Well, the first one we're asked to do that with is the logarithm of 9 base 3 is equal to 2. Now, what we have to recall is the similarities. That is, when we say the logarithm of x base a is equal to y, that's the logarithmic form. Then the exponential form is a to the y is equal to x. So the base, so we're going to write this in exponential form. The base is 3. That's what we put the exponent on. What the logarithm is equal to, that is the number on the other side of the equal sign, what the logarithm of is equal to is the exponent. So 3 to the second power is equal to, well, the argument of the logarithm is what we're taking the logarithm of, and in this case 9. So 3 to the second is equal to 9 is the way we would write that in exponential form. Second example, the logarithm of 1 base e is equal to 0. Now, we're just changing the form. We're really not trying to determine whether these are true statements, but each of the ones I write will certainly be true if they're filled with numbers. So in this case, e is the base. E is the base, and certainly we know from previous lessons, e is 2.7 something, so certainly it satisfies the conditions that are required for a base of a logarithm. So we have the base e. Now, remember the exponent's what's on the other side of the equal sign. In this case, the 0. And of course, that has to be equal to what we're taking the logarithm of. That is the argument of the logarithm. And of course, we know that's also true. Some number to the 0 power is certainly equal to 1. Okay, the next example. The logarithm of x base 10 is equal to 1.2. Now, we're not going to be able to verify the accuracy of this statement. All we're doing is writing it in exponential form. So this time the base is 10. The exponent is the 1.2, and that must be equal to, then 10 to the power 1.2 must be equal to the argument x. A couple more. The logarithm of 1/8. The logarithm of 1/8 base 2 is equal to -3. The exponential form of that would be 2, the base, to the power -3, that's on the other side of the equal sign, is equal to the argument 1/8. And of course, we recognize that that's a true statement as well. Okay, the last one of this type, the logarithm of 2 base 5 is equal to x. So don't get confused with the position of the x's and y. I mean, where an x is, look more at its position. So the base this time is a 5. And what the logarithm is equal to is an x. So x is the exponent in this case. And so that means 5 to that exponent, 5 to the x power, is equal to the argument in this case, which is 2. So we've converted each of those into exponential form. In the next set of exercises, we're going to go the other direction. We're going to be given something in exponential form and write it in logarithmic form. And we'll do that on the next page. Okay, so the first example, we're going to write in logarithmic form. We're given 10 to the second power is equal to 100. Now, once again, let's compare what we had before. If we had the logarithm of some argument, base a is equal to some exponent y, then the equivalence of that would be the base a to the power y is equal to x. And so when we go to convert this, we've got to remember in a logarithm, there's 3 positions that we have to fill in. And the subscript is the base, which implies what the exponent is actually on. And in this case, that's a 10, isn't it? And what the logarithm is equal to, that's on the other side of the equal sign, is actually the exponent. And so the exponent that we see here on 10 is a 2. So the 2 goes in this position. And of course, there's only one number left over, and that's the 100, which is the argument. And so we read this. The log of 100 base 10 is equal to 2, which means 10 to the power 2 is equal to 100. And let's convert a few more here. How about 10 to the power -2 is equal to 0.01? Well, if we're converting that, again, we just have to remember where are the places we fill in. First, we look for the base, and that's what the exponent's on. So we put the base of the logarithm in this position. Now the exponent is what goes across the equal sign here, and in this case the exponent is -2, and the argument then is what 10 to the -2 is equal to. In this case the argument, of course, goes in this position. Okay, another one. 3 to the 4th is equal to 81. Well, you could probably work ahead here or pause and write this out. But here we'll have a logarithm. In this case, the base is 3. That's what the exponent is on. And the exponent is 4. That goes over here. And what's that logarithm of then? The argument of 81. A couple more that have variables in them. For instance, e to the x is equal to 1.2. Well, this time what the exponent is on is an e, so that's the base. What the exponent is equal to is an x, and so the argument is the 1.2 that we can fill in. Last one of this type. 2 to the power 0.03 is equal to x. So once again, the base we look for first, that's what we put as the subscript of the logarithm, and the base is what the exponent's on, and that's a 2. The exponent goes on the other side because the logarithm is equal to an exponent, and so the exponent 0.03 goes to the right here. And of course the argument is what we're taking the logarithm of, and in this case that's the part that's left over. So we read this as logarithm of x base 2 is equal to 0.03, which is equivalent to saying if we take this base 2 and we put this exponent 0.03 on it, we're supposed to get the value of x. That's the 1, 2, 3 kind of, 1, 2, 3 kind of the way I look at that. Well, another thing that we need to be able to do is to evaluate or find the value of logarithms. And in the first set of, the first few examples, we can just kind of think this out. And so here are the directions we're dealing with, though. Find the exact value of the following, of each of the following. Well, our first one is the logarithm of 5 base 5. And so we want to know what that's equal to. When we say find the exact value, what's that equal to? And so remember where that question mark is really going to be an exponent, isn't it? And so if we take the base, which is 5, and we put that exponent that's under question yet on it, and we're supposed to get the argument, which is 5, then real easily we can say, well, 5 to what power is 5? And so we can figure out that that power has to be 1. And you know, this is kind of, we could do this more generally, because we could say, well, what's the log of a base a? What power do we put on a? What power do we put on this base a to get this argument a? And that would be 1. So if the argument and the base are the same, then the value of the logarithm will be 1. Well, let's look at this next one. The logarithm of 1 base 1.2. What is that equal to? And that's the question here. So remember, this time the base is 1.2, and the question mark, that is the question mark is really what exponent, isn't it? So we want to know what exponent we put on 1.2 to get the argument of 1. So there's kind of a magic exponent, isn't there? That if we put an exponent of 0 on any number except 0 itself, we will get a 1. So from that argument, or from that description, we can think, oh, well, in this case, yes, 1.2 to a power of 0 is equal to 1. So that's the value of this logarithm. Now, this also says something pretty important, because it would tell us that the logarithm of 1, no matter what the base is 0, because a to the 0 will be 1. So the logarithm of 1 is always going to give us a value of 0 regardless of the base. So keep that in mind. Okay, the logarithm of 27 base 3. What's that equal to? So our base is 3. We want to know what exponent we put on 3 that will give us a 27, and it doesn't take us long to figure out that that in fact is a 3, does it? Okay. Now, I'm going to take a twist. I'm going to pause here and do, since we already know the result here, do this particular one a different way. And because a couple of these that follow, this may be a useful tool for us. So let me explain to you here that I could have converted this to exponential form. And if I convert it to exponential form, now, of course, let me first start out, I guess, before we have the answer. I'm looking for the answer, and I'm going to call it n. And that's what we actually convert to exponential form. I got a little bit ahead of myself, okay? And so in this case, exponential form would say, oh, we'll take the base 3, raise it to the power n, and that's got to be equal to 27. And I recognize that we already know what n is in this case, but this is very similar to solving the exponential equations that we did just before this section. And what we might do here is we might write both sides so that they were 3 to the power. And so we look at 27 and say, is that 3 to the power? Oh yeah, that's 3 to the third power. And so now we have an equation, 3 to the power n is equal to 3 to the power 3, and from that we conclude that our n value is 3, and so we would have known the result here was going to be 3. Now, like I said, that becomes more useful the more complicated some of these evaluations or find the exact values become. Let's continue this again on the next page. Okay, here's our next one. The logarithm of 1 over 49 base 7. And we might be able to figure this out without a great deal of trouble, but I want to do similar to what I did last time and say, well, okay, I don't know the result. Let me say that it's n, and then let me write this in exponential form. I'm going to convert, okay, to exponential form. And when I convert the form, then I'll have 7, the base, to the power n, which is what I'm looking for, is equal to 1 over 49. Now that still doesn't solve it directly, but I notice a relationship between the 7 that's a base on the left side and the 49 that's a denominator on the right side. Certainly we know that 49 is 7 squared. And so now I have some hope of writing each side as 7 to a power. 1 over 7 squared is 7 to the power negative 2. And of course now I would know, oh, well, that means n itself has to be negative 2. So that tells us the logarithm of 1 over 49 base 7 is equal to 2. Now this is really all building up to this particular problem. What is the logarithm of 9 with a base that's the square root of 3? Now, in all of the ones before, we might have guessed or thought through in our head the correct exponent to put here. But probably for most of us, we have no idea what that exponent is going to be. So let's call it n once again, okay? And let's convert to exponential form once again. So in this case, I would have the square root of 3 as my base and a power of n on that base, and that's equal to 9. Now, I have an exponential equation. And certainly it's not so easy to write 9 as the square root of something, but I can certainly write 9 as 3 squared. That's not a problem. Now, the significance there is on the left side, I have the square root of 3, but the square root of 3 can be written as 3 to a power of 1/2, can't it? So I could replace square root of 3 as 3 to a power, and then on the left side, I could apply rules of exponents where I multiply the power 1/2 and the power n, and so I would have 3 to a power that is n over 2 is equal to 3 to the power 2. And I've succeeded at having 3 to a power on each side, which means the power n over 2 must be same as the power 2. And then I have a simple equation I can solve. I'll just multiply both sides by 2. And so I end up with n on the left side and 4 on the right side. So my value n is 4, or in other words, the logarithm of 9 base square root of 3 is equal to the number 4. So you see it was useful to do that conversion in this case. Now, I want to point out that there are 2 special bases, and I may repeat this at a later time, but there's 2 bases, okay, of logarithms. whoops, logarithms. And they are base 10 and a base of e. So back when we saw, and let me tell you what the special, those bases are used frequently. Let me go back to a problem that we had before. I think we had something like the log of 100 base 10 is equal to 2. Whenever we see a base 10, it's called a common logarithm. Now on either your graphing calculator or your scientific calculator, you'll see a key that just says LOG, capital LOG, and that stands for a common logarithm. We use this base 10 so frequently, we have a shortcut way of writing it. When the base is left off completely, like we see here, that means base 10. That's kind of like leaving the little index off of a square root. When we say square root of 9, we don't put that little index of 2 up there because square roots are used so frequently. So if we don't see the base, it's a common logarithm. And we saw another example where we wrote it out. Let's see, I think, what did we have? I'm looking at some of my old examples, and I think I had the logarithm of 1 base e is equal to 0. Now, base e, again, is another very special logarithm base, and whenever we see base e, that's called a natural logarithm. Doesn't seem so natural, but it actually occurs quite frequently in nature when we talk about decay and population growth, like the growth of a colony of bacteria or something. Now, once again, because it is used so frequently, we have a special way of writing it. And we've already written something without a base at all, so in this case, we don't write the base, but we change the log to an ln for natural logarithm. So we might say the natural logarithm of 1 is equal to 0, which means the same thing as logarithm base e. So we have to keep that in mind. Also on your calculator, you will see an ln key, capital L, capital N. And that's the ln that we're seeing here, and that means logarithm base e. Those are the only two bases that are on your calculator, by the way. Well, as we follow through on this discussion, I guess the next thing we want to know is how we graph, what the graphs of these logarithmic functions or functions that have a logarithm might look like. And so we'll continue that on the next page. Well, we want to graph some logarithmic functions. First, we'll start out with the very basic logarithmic function, and then we'll use transformations on graphing things that are a little more complicated. And we want to pay attention when we're finished doing the graph to what the domain of the particular function is, what the range is, and any asymptotes that may exist. So let's begin by just thinking about trying to plot some points, and understand that this may be more difficult than we first realize here. So we're graphing y equal log of x base 2. So we might choose x to be 0. And if we did, then we would be trying to calculate y, which would be the log of 0 base 2. That would have to be what y is, wouldn't it? Now, let me point out to you that this is a big problem. Because that would mean, if we take the base 2 and put the exponent y on it, we get 0. But there's no exponent out there that we can put on 2 that will give us a 0 result. So this is a big issue. Okay, 0 is not in the domain. Likewise, if we choose x to be -1, we might not have done that right away, but then our y would be the logarithm of -1 base 2. And that would mean 2 to the y would have to be -1. And we have the same problem, is that there's no exponent we can put on 2 that will result in -1. I mean, positive exponents on 2 just give positive numbers. 0 as an exponent on 2 just gives a result of +1. And negative exponents on 2 just give 1 over 2 to a power. So they're just fractions, but they're positive. There's no exponents that we can use that will give us a -1 result. In fact, there's no exponent we can use that will give us any negative result. So we need to maybe stick to x's that are positive. And so we choose x to be 1. And if we do, then we have y is the logarithm of 1 base 2. And so in that case, we're saying 2 to the y is equal to 1. So what is y? Oh, it has to be 0. And then we might choose x to be 2. And if we did, then we would have y is equal to the logarithm of 2 base 2, which would mean the base 2 to the exponent of 1 has to give us a result of 2. And so the only way that can be is if y is 1. Now, we hit 3, and we've got a problem. We don't know what exponent, see, this would be getting kind of short of space here. This would say that y is equal to the logarithm of 3 base 2, and that would mean 2 to the y is equal to 3, and of course, we have no idea what y makes that happen. So we don't have a good result there. Now we'll try 4, and that would be y is equal to the log of 4 base 2. That is what exponent we put on 2 to get a 4, and that would be 2. If we try a 5, we'll have trouble. If we try a 6, we'll have trouble. But if we try an 8, then y to the power 8, okay, 2 to the power y being equal to 8 would tell us, see, this is what we've got. Y is equal to the logarithm of 8 base 2, which means 2 to the power y is equal to 8. So what is the power y? It has to be 3. Now, in a similar fashion, we probably need to choose some other types of, well, let me begin graphing, and then we'll describe a little later what we're more concerned about, what we're further concerned about. So let me pause here just to get the graph set up. Okay, I've got a coordinate system set up here. So let's plot 1, 0. This is 1, 0 right here. Let's plot 2, 1. Here's 2, 1 right here. 4, 2. 4, 2 is here. And 8, 3, which is out here, right there. Now, let's stop and think here again, okay? I'm trying to make a big deal out of this. Remember from the argument we had just a moment ago that we can't take the logarithm of 0 because that doesn't make sense. And we can't take the logarithm of a -1, that doesn't make sense. And so, in fact, let me make another point here. The logarithm of 0, regardless of the base, is impossible. And the reason it's impossible, okay, it's undefined. Because if this was y, that would mean a to the y power is equal to 0. And in this case, we're talking about 2 to the y power, but a number to an exponent is never going to give us a 0 result. Never, ever, ever. This is impossible. So we can never take the logarithm of 0, okay? Make a point of that. That's a big deal. The logarithm of 0 is impossible. Likewise, the logarithm of a negative number is also impossible. Now, we looked up there specifically for the logarithm of -1 base 2. But more generally, if this was the case, that would mean a to the y power is equal to some negative number. And you can think all day long as you want, as long as a, remember, a is a positive number itself. Our bases are positive. So as long as we have a positive base, no matter what exponent we put on it, we're going to get a positive result. So that means it's impossible to take the logarithm of a negative number. That's impossible. Okay? Can't ever do it. So when we're looking at choosing x's to make this graph, we can't choose an x of 0, and we can't choose an x that's negative. But there are lots of positive numbers between 0 and 1 that we can choose for x. For instance, we could have chosen an x value of 1/2. See, that is an okay x. That's not negative and it's not 0. So that would mean y is equal to the logarithm of 1/2 base 2. And that would mean 2 to the y power is equal to 1/2, and that would mean y has to be equal to negative 1. So we've got an additional point. X is 1/2, but y is negative 1. That's this point. And we could have chosen x to be 1/4. Well, in that case, that would mean y is the logarithm of 1/4 base 2, which would mean 2 to the y has to be 1/4, and that would mean y has to be negative 2. So our y can be negative 2, but our x can't be negative. So now we have an x that's 1/4, that's just a little bit bigger than 0, okay? And our y is negative 2, so that's down here, isn't it? But right there. And likewise, we could have chosen y to be 1/8. In that case, we would have got an our x to be 1/8. In that case, we would have y of negative 3, which would be down here. So this graph looks like this. Oops. Now, x can't be 0, but we can choose x's closer and closer to 0. And that's why you see that graph getting closer and closer to where x is 0. That's the y-axis, isn't it? Now, if we look at this graph, we certainly can tell that the domain for this particular graph, is going to be all x's greater than 0. Now, in set builder notation, okay, we write that as the set of all x's such that x is greater than 0. Can't be equal to 0, can't be negative numbers. Or we can write it in interval notation from 0 to infinity. Those mean the same thing, don't they? And if you look at the range, the graph continues to go up on the right. It just goes up slowly. The graph continues to go down on the left. It goes down pretty quickly, but you can see that all y's are going to be used. So the range is all real numbers. And in interval notation, of course, that's from negative infinity to infinity. Now, in this case, the graph is getting closer and closer to the vertical line, which is the y-axis. And this graph has a vertical asymptote. Oh, I'm about out of ink. Let me pause and change ink. Okay, sorry for the delay there. We have a vertical asymptote. Now, the graph doesn't get close to this vertical asymptote on top and bottom, just on the bottom, doesn't it? But the vertical asymptote is the vertical line x equals 0, which in this case is the same as the y-axis, isn't it? I mean, x equals 0 as a vertical line is the y-axis. Okay. Now, I want, well, stammering here. I guess I want to make a summary on the next page, okay, is what I want to do. And, well, I guess we'll just stop here, actually. If I'm graphing, well, I apologize. I want to make a summary on the next page. So, more generally, we looked at one specific basic logarithmic function, but as long as we have a base that's positive, greater than 0, that's our a, and it's also not equal to 1, then the graph of the log of x base a will look similar to what we just saw a moment ago. And that similarity then means it will go through this point. This is where x is equal to 1, and it will rise slowly as we go to the right. And of course, we can't have our x's being 0 or positive, so they will all have this similar look. And the domain in all these cases is that x has to be greater than 0. And the range in all these cases, when we're talking about this specific type of function, is all real numbers. And we have a vertical asymptote, which is x equals 0, which is the y-axis, isn't it? Now, using that information, then we can graph using transformations. So let's graph by transformations. Now, before we actually do a graph, let me point some things out, just so that we'll be prepared for the different kinds of pieces. So if we look at y equal the logarithm of x base a plus a3. Now, to make this clear, we're really just taking the logarithm of x, not of x plus 3. So I need to make that clear. This is a vertical transformation. That plus 3 causes a vertical shift. Okay. On the other hand, if we had y is equal to the logarithm base a of x plus 3, that is, we're taking the logarithm of x plus 3, not the logarithm of x and then adding 3 more to get our y. This is a horizontal transformation. Horizontal shift. If we have the opposite of the logarithm of x base a, this is a reflection, x-axis reflection. And if we had y is equal to the logarithm of the opposite of x base a, this is also a reflection, but it's a y-axis reflection. So let's look at a couple of examples. Sketch the graph. Y is equal to the logarithm of x plus 2 base 2. So we note this is a horizontal shift, but it's plus, so we shift 2 units left, don't we? So what we start out with is the graph of y equal the logarithm of x base 2. So here's the 1, and so we start out with the graph that we know what looks like. Okay, and remember, this is what the y equal the logarithm of x base 2 looks like. And we're going to shift that 2 units to the left. So I'm going to pay attention to this point. I'm going to shift it 1 unit. I'm going to shift it 2 units. So this is where -1 is. Okay, and then my graph, okay, now let's stop and think about this. This graph doesn't continue, our original graph doesn't go to the left forever. So when we shift it, it won't go to the left forever. So the line, the vertical line that our original graph is getting close to is also shifted over 2 units. So that means this line is this vertical asymptote shifted over 2 units, so that would put it there. So this is where our new vertical asymptote is going to be. And this point gets shifted to here. The point here gets shifted to this position. So now when we sketch this graph in, it will look like that. Okay? Now let's consider here our different pieces. What's the domain in this case? Well, now we've had our graph shift. And so the domain are the set of all x's that are greater than -2. They're never equal to -2, but they're greater than -2. And of course, in set builder notation, that would look like the set of all x's so that x is greater than -2, or in interval notation, that would look like -2 to infinity, but do not include -2. Now, don't get confused. If x can't be -2, but it could be -1, or it could be -1.5. Now, we're not, if we use that x, be careful about this, because you may be thinking, oh, I can't use negative x's. We just talked about that a while ago. Well, no, we can't use negative x's if we're taking the logarithm of x alone. See, if we choose x to be -1, then in this case, our y is the logarithm of a -1 plus 2, base 2. And of course, -1 plus 2 is a positive 1. So that x doesn't mean we're taking the logarithm of a negative number. We're actually taking the logarithm of a positive number with that choice of x. Our range has not changed. Our range is a set of all real numbers. So we could say -infinity to infinity. And in this case, our vertical asymptote, though, has shifted, hasn't it? Our vertical asymptote is the line x equal -2. And we can mix, let's look at another couple quick ones here. And we'll do that on the next page. Well, you can see here we have, we're asked to sketch the graph of y equal to the negative of log of x plus 3. And so the two transformations are the minus in front of the logarithm and the plus 3 after we've calculated the logarithm. And and we have to remember the order that we would do this in. This would be the first transformation we're worried about, and this would be the second. And this first transformation is an x-axis reflection. And the second one that we're worried about is a vertical shift of 3 units. So, actually I didn't even write down the base, did I? This could even be a base 5. Let's do that. And so what we have to start with is what would the log of x base 5 look like generally? Okay, just what would it look like generally? So I'm thinking graph of y equal to the log of x base 5. And what I know is it'll go through this point, which is 1, 0. Okay, it goes to that point. And then it looks something like this. I'm not trying to be precise here, but it would look something like this, wouldn't it? Okay. Now, this very first x-axis reflection would make everything that is below the x-axis be above and everything above the x-axis be below. So that very first transformation would cause our graph to look like this. See, this is after transformation 1, which would be y is equal to, the opposite of the log of x base 5. And then we're going to take that graph and shift it up. The second transformation is we're going to shift it up 3 units. So I'm following this point again. Here's 1, 2, 3. And that point's going to be shifted up here. And so my actual graph then is going to look something like this. Okay, this is actually what we're graphing. Y is equal to the opposite of the log of x base 5 plus 3. Now in this case, what's the domain? Well, in interval notation, the domain is all x values greater than 0. And so we would write it this way. And the range, in this case, the range is still a set of all real numbers. And the vertical asymptote here, well, we only shifted upward. And so since we didn't shift left or right, the vertical asymptote stays in place. And so the vertical asymptote is the line x equals 0. Let's do one more. Let's sketch let's say, how about y is equal to simply the log base 3 of negative x. Now, there's only one transformation here, and if you recall, this causes a y-axis reflection. And so we start out with what y equal, remember, if we start out with just y is equal to the log of x base 3, we don't need to be real precise here, but that graph would look something like this, wouldn't it? We said they all look similar to this. Of course, this is the y-axis and this is the x-axis. Now, if we reflect that about the y-axis, then what was over here at 1, 0 will be over here at negative 1, 0. And so a reflection in this axis would look something like this. Okay, well, what's the domain here? This is completely different. The domain here is all x values between negative infinity and 0. In other words, we can only use negative x values. So why does it make sense we can use an x of negative 9? Because y would be the logarithm of the opposite of our x, so it would be the opposite of negative 9 base 3. And so that would be the log of positive 9 base 3. So since we have that negative in front of the x's we choose are going to have to be negative. Our domain is a set of all negative numbers, basically from negative infinity up to 0, but not including 0. Our range is the set of all real numbers once again, and our vertical asymptote has not changed. It is the vertical line x equals 0. Now, you can put together some more examples, and you will be asked to do that, obviously, in your homework. I want to pay a little bit more attention here to the domain of logarithmic functions in general. We've seen in each of these examples, we've looked at the graph and then we've decided the domain, but we can determine the domain before we ever even graph. Well, a moment ago, we were asked to graph y equal the log of x plus 2, and I've forgotten what it was. Was it base 2? It doesn't really matter, the base in this case. So find or determine domain, okay, in this case, determine the domain. Let me write it in function notation of f of x equal to the logarithm of x plus 2 base 2. Now the base 2 and the plus 2, that's just coincidental that those are both 2. That's only coincidental here. Now here's what I remember what we talked about earlier. The logarithm of 0, regardless of the base, is not allowed. That just doesn't make sense. And also remember what we talked about at the same time is the logarithm of a negative number is not allowed. Now, and remember what we're taking the logarithm of is called the argument. So the whole idea, pardon me, in general is the argument. Okay, the argument, that's what we're taking the logarithm of, can't be 0 and it can't be negative, so that means the argument must be positive. And the way we write that algebraically is argument is greater than 0. That means positive. So when we're looking at the function f of x is equal to the logarithm of x plus 2, base 2, remember this is the argument. And the argument must always be positive. So the way we find the domain, the way we calculate the domain, is that we say, here's what we know. The argument, in this case x plus 2, has to be greater than 0. So we end up solving an inequality. And of course, to solve this inequality, we would what? We would just simply subtract 2 on both sides, wouldn't we? And we'd end up with x is greater than negative 2. And if you look back at our work, when we did our graph, we determined that the domain was the set of all x's greater than negative 2. And this is a way we could have done it simply algebraically. So the domain in interval notation would be from negative 2, but not including it. That's the reason for the parentheses, to the right forever. Greater than negative 2, so to the right forever. So we put an infinity there. We calculated that rather simply. And that's the way we would do it for any logarithmic function. Now, there are a couple of more things that I want to do while we're in this section talking about graphing. Yes. Let me show you a couple more graphs, and I'm going to set this up way in advance here, and I'm just going to do that on the next page, and then after that we'll solve some logarithmic equations. Okay, we'll solve some logarithmic equations. So what I'm going to do on this page is compare the graphs of y equal the log of x base a and y equal a to the x power. And more specifically, for an a, in this case, that's 2. Okay? Specifically, an a, so we have y is equal to 2. So the logarithm of x base 2 and y is equal to 2 to the x. And what we're going to see is that these are inverse functions. Okay? And that's the big deal. And I want to set it up so that it's easy to see that. These are inverse functions. They're inverses of each other. Okay? So first I'm going to plot some points for y equal 2 to the x. And we've been through this. And so let me fill some in. Let's fill several in at a time. You can see I filled in a solution table for the function y equal 2 to the x. Also, for y equal the logarithm of x base 2, I'm going to do the same. Now, I've calculated these, but you could also look back at what we've already done. In both of these examples, y equal 2 to the x we did in a previous lesson, and we just graphed a moment ago y equal the log of x base 2. And you can look and see that we got these same, this same set of points. Now notice from the points that the order of the x and y's in each case have been reversed, haven't they? And that's an indicator of having inverse functions. So next what I'd like to do is plot some of these points and draw the appropriate graphs. And so I'll do that a little lower here. I think I'm going to do one more thing before we do that. Let me pause to set this up. Over here on the right, you can see I've drawn kind of a little diagram. Remember, the relationship between inverse functions is the domain of one is the range of the other, and the range of one is the domain of the other. In y equal 2 to the x, we decided the domain was the set of all real numbers. That's what that double barred R is. That stands for all real numbers. And we saw that the range were all the y's greater than 0. On the other hand, the domain of y equal log of x base 2 was all x's greater than 0. Now, of course, here we see range and domain are the same, except the range are y values and the domain are x values. So that variable name had to change. And we decided the range of the log function is all real numbers. But of course, here we're referring to y's. Above, where we have the domain is all real numbers, we're referring to x's. But the fact that they're all real numbers corresponds. Now, if we look at these graphs, which I'm going to do next, let me pause temporarily. Well, I've sketched in both graphs, and maybe it's not quite clear yet, so let me graph the line y equal x. So it'll go through 0, 0, goes through 1, 1, goes through 2, 2, goes through negative 1, negative 1, and when I sketch that line in, remember these graphs of inverse functions are symmetric to the line y equal x, and you can see that appear right there. So certainly I haven't proven it, but all the, if you will, there's plenty of data to imply that these two functions are inverses of each other, and in fact they are. So that's the big deal. When we have these two sets of functions, if they're the same base A, then they'll be inverses of each other. Okay, we're going to conclude this section by solving some logarithmic equations. So let's do that on the next page, 12. Okay, as you see here, we're solving some logarithmic equations, and this is just an introduction to solving logarithmic equations. Later on, and we'll solve some that are much more complicated, but let's begin. So the very first one I want to solve is the logarithm of 5x plus 6. And so we put that in parentheses because it's the 5x plus 6 that is the argument. Base 2 is equal to 2. Now, normally the way we solve a logarithmic equation of this form, that is where we have a logarithm, a single logarithm on one side is equal to a number on the other side, the first thing we'll do is to convert. That is, we'll convert this to exponential form. And as soon as we do, then it will become obvious what to do. So in exponential form, we take the base, which is 2, we put the exponent over here, which is 2, on it, and that must be equal to the argument, which is 5x plus 6. I'm just going to turn that around, because that's the way I like this. I'm going to put my 5x plus 6 on the left side, and 2 to the second power, of course, is just 4. And so now, to solve for x, we have a simple equation, don't we? We would simply subtract 6 on both sides, and we'd end up with 5x is equal to negative 2, and so we'd simply divide both sides by 5 and have x is negative 2/5. Now we have to be careful though. Be careful. I don't think this will be a problem right away, but does x equal negative 2/5 make sense? See, because we know that we can't take the logarithm of something that's 0 or negative. So what we need to really do is check out what would happen if we replaced x with negative 2/5. See, what would really be going on there? Like if we were going to check this. Well, let's see what we would get. 5 times negative 2/5 is negative 2. So we have a negative 2 plus 6 here, base 2. And negative 2 plus 6, of course, is 4. And so we're kind of saved here that because negative 2 plus 6 is 4, and 4 is a positive number, it makes sense to use an x value of negative 2/5. In fact, we could go further here and say, oh, well, I know the logarithm of 4 base 2 is 2, and that's what we were supposed to get, isn't it? So we've actually checked at the same time. Okay, let's solve another one. Let's solve the natural log of e to the x power is equal to 8. So we need to know the x value that makes that true. Well, the only difficult part about this problem is that we just haven't seen anything quite like it before, and we're not used to all the notation. So let's remember, let's kind of make a side note over here. This natural log e to the x is another way to write the logarithm of e to the x base e. See, that ln, natural log, really means log base e. So temporarily, I want us to be able to get away from having to write this extra step here, but that's really what we're dealing with. So we'll convert again, and as soon as we convert, we take this base and put this power on it. So we have e to the 8th power is equal to the argument, which is e to the x. Well, then what's going to make that true? The only way that can be true is if two exponents are equal, and that would be that x is equal to 8. So we have our, by the way, I'm going to circle the solution up here. We have our solution automatically, don't we? It was simpler than it first appeared. Well, I think this should get you started real well on the section dealing with logarithmic functions and their graphs and domains and solving a few basic logarithmic equations. Good luck to you.